start.
Hey, good to see you. I'm all right. I guess this is the only place you can show up. You look like you've been really busy.
Hello, everyone. This is Computing in the Network Coin. We're going to get going just a few seconds. If you're not here for Coin, please stay anyway. We have a great program. And if you are here for Coin, well, you're in the right place. We still need someone to take notes. I had sent a request this morning and nobody really answered. So if somebody who is not presenting could actually be the good Samaritan and take notes, it would be greatly appreciated. If not, I'm going to name I may name a volunteer. So anyway, please, if somebody can take notes, just raise your hand. And we're going to get going. Rachel, thank you so very much. So, great hand for Rachel. Okay, so this is
It's funny, the microphone, no, the microphone doesn't work.
Okay. Hi, I'm Eve Schuler, and these are my co-chairs, Marie-José and Jeffrey. Welcome to the Coin Working Group. This is our second official meeting, our third gathering. Of course, we started with BOF. We're still in proposed research group mode, and we're grateful to see so many of you out there and so many contributions. You're in the IETF, IRTF, you know this note well, slide well. Things you should know. Our data tracker, where all of our documents are, our charter, our milestones. We're in the middle of migrating basically from a wiki-based mode of sharing information to a GitHub document archive as well as code archive. And the Coin mailing list is simple to remember, coin@irtf.org. And we have remote participants today. We're going to have a remote presentation. And we've just appropriated our own Slack workspace, which will also allow us to have interim meetings more easily. We have a full agenda. We have basically many internet drafts. Many of them will be presented today, at least the new ones. I think we've got 8 at this point in time, and 5 of which will be presented today. In addition to the administrivia, we'll talk about next meetings that are going to be happening. And I think the only change to these presentations is that Dirk and Jörg have a combined merged presentation based on their draft. Yeah. I think it's you. Okay.
So this is Jeffrey. For those new to this group, so the general goal of this group is to foster research in computing network to improve performance. And our focus will be network architecture and protocols, and by addressing real-time use case applications and work in progress. So we have modified the chart a little bit after Prague and June interim meeting, and also based on the discussion in mailing list. And thanks for the contributors and the participants. So main change now is on the items in scope section, as you can read in this slide. But the plan is to capture potential proposals from this meeting and maybe after. Then we will have a revised version submit to IRTF chair to review and approve with the consensus of this group. So we also are working on some milestones, very preliminary. We know this is we still are proposed RG, so it will not take effect unless we are approved as a formal one. But we hope to use this to check some discussions on the future plan. So we suggest to capture the state of the art and articulate some challenges, then target the use case and also identify the ecosystem dependency and also the requirements. Then hopefully we can have a specific coin scope maybe later next year and specific enough so that within which new architecture and mechanism and protocols can be proposed. We are also link the existing individual draft to these milestones, just as related drafts. So basically, the input to the discussion of each part. It's not. We are not implying this will be a potential formal research group draft, right? It's too early to see that. Okay.
So yeah, while we're just a proposed research group, we're kind of lucky that we've had a bunch of people ready to do work that addresses the issues that we want to do. So we currently have, as you can see, 4 new drafts, which was really good for this meeting. And we have 3 existing drafts that were updated, and we didn't have time to put them on the agenda for today, but they're progressing. Especially the one on XR is going to be also taken over with a new team to make it progress. The other one, we have stuff on industrial networks, on actually the problems of coin, two drafts on that, and then the App Center we have two Dirks here. So we have Dirk number 1 on what coin is, and we have Dirk number 2 on the App Centers. And so this is going to continue, and obviously collaborators are welcome. And if you have other ideas for drafts, please supply them. So we had our first hackathon on Saturday, and this is the present of people who participated. And we had, I think our hackathon could have been some kind of a train wreck because P4 is this new language that allows you to program switches, and there's not a lot of people who know how to do that. And we were very, very lucky that there is a local company called Noviflow who has its business of doing P4, and they lent us 2 engineers for 2 days. So thank you so much. And they actually got us going, and so they're around the table with the team. So it created a really, really nice team. We could also poach a few people from other tables, so ended up having quite a large number of people. What we did, obviously there had been P4 hackathons and P4 tutorials and other conferences, so we could actually take basic examples to get everyone on board. We had a remote participant who actually was the guy who knew how to program this, so he had his own project on machine learning in IPv6, and he made a lot of very good progress on this. We had, I don't know if he's here, but we had somebody from Liquid Telecom, which is from Africa, who recognized that he could actually do some translation of P4 to Golang, which is the language that they use on their networks. At the end, we after one day where everybody was actually kind of up to date in how to do things, we had 2 participants who addressed a real problem that actually we're going to face both in industrial networks and in this XR AR/VR field, which is actually packet filtering. So compare a packet to I called it the original idea was to have a perfect packet and then compare all the other packets to it and make sure that we can detect when there's something interesting. Obviously, we didn't do that. We started by comparing addresses, so we're storing one and comparing. But just to tell you that after one day, people were really, really ready to do real work. And we also made a list of ideas, and I'm going to post that on the GitHub. We have the pictures. What we learned is that the need to come prepared is really good, especially when you're going to do everything in virtual machines. The usefulness of experts in a field that's expanding. I don't know how many hackathons are in a field where the language is not even fully defined right now, so it was really good to have people who knew what they were doing. You can get participants the same day, so that was great. People were seeing what we were doing, and they were joining the team. You do a lot in 2 days, which was surprising in a way, and the teamwork was great, and we have now a shorter mailing list of all the people who participated in the hackathon to continue the work that was started. And we plan to have another one in Singapore, so if you're interested, you can join us. So now we have a ton of presentations, and we have instructions to the presenters. And I see Dirk saying, oh, you didn't tell me this. So this is a surprise. So the instruction to the presenters is, if you can, please try to link your work, and that's not going to be difficult for you, Dirk, to the charter, and highlight maybe where changes would be necessary. And yes, so you're next up. And if I'm lucky, I'm going to be able to load your slides.
Thank you. You don't have to call me Dirk number one. That's, I think, would be a bit. No. That's much better. Okay. Thank you. Yeah. So the intention of the draft that is mentioned here in this presentation is actually to provide input to your planning process and discussion. To be honest, I was a bit surprised to see such a detailed list of milestones. It's good, but no, I mean, in my experience, a research group probably also takes some time to find directions, and I think. Oh, it's too low. Yeah. Okay. And. So this draft and presentation is trying to provide some input on, say, potentially interesting topics, and also derive some research questions that could be of interest. Okay, let's get going. You got it? Okay. So I'll talk a bit about what does it actually mean when we say in-network computing. So computing missing, and then we discuss a few thoughts. Technical aspects, and we end with some perspectives on what could be really interesting to do in Coin. And okay, so I mean, there's lots of computing in the network already today. So we heard about SmartNICs on Monday. Where web servers do computation. CDN is kind of a computing system as well. All these cloud platforms. Often you hear the term edge computing, and this is a really fuzzy term. And what it typically actually means is extending well understood and widely successful cloud computing concepts to the edge. So I would say there's potentially not that much research to be done there. Architectures like mobile edge computing, so they look kind of intriguing, or at least unusual. But this is essentially just extending cloud computing, virtualization technologies, and management technologies to execution platforms at the edge that do something with like edge systems like radio. Base stations, for example. So it's nothing really new, and I don't think so. Virtualization and automated management for these kind of systems are particularly interesting for us. Then there is this whole category of also widely successful application layer streaming, event processing, data analytics platforms. So this is Apache Flink here. So they're also used all over the place, and all the say popular web servers are powered by them. So they run in the cloud. They run in overlays in networks where network is relatively cheap, over provisioned, and well managed. So when you think about doing similar things, say maybe in less well controlled, more distributed, say internet scenarios, there could be an interesting edge there. So these overlay systems, I mean, they benefit from all the internet tools that we have, transport protocols, TLS, and so on. But they essentially treat the network as overlays, and as such have relatively limited visibility into the network. So you could actually say they treat the network as circuits. They use different namespaces, have to translate between them. So this works well in the cloud and data centers. Would be interesting to see what can the network do to support these systems, say, more directly. And so earlier, I think in previous talks, we talked about this idea of doing that by jointly optimizing computing and networking resources. So for example, if you want to make a compute offloading decision, you just do not allocate any available VM, but maybe you do this based on knowledge about the topology, congestion, historic performance, and so on. And so you have a system that basically can do many decisions in the network itself, can maybe also leverage mechanisms that the network actually already has, so like routing protocols, for example. Let me just glance over this a bit quicker because I said this. So now when you try to implement this joint optimization, for example, or this integration of computing and networking, there are different candidate technologies you could look at. So service function chaining is one. So we have a talk on it later, so I won't say too much. But so functioning is basically the idea that I arrange, say, a path from that touches several network elements in my system, with the assumption that these elements can do something useful or need to see the packets in the flow. And so these are functions like classifiers, filters, caches, and so on. Normally, these systems are fairly statically configured, so they don't change that often. You can reconfigure them, but it's not the idea to switch like next hops all the time. And typically, the assumption is that also we actually don't get in between the TCP end-to-end control loop. It's more like on a packet level that what you do there. Okay, so this is intended for specific operator, so-called GA-LAN scenarios, not exactly a platform for distributed computing, but I'm interested to see, say, what our colleagues have done in the next talk. Then you just talked about the P4 work at the hackathon. So there is this work on using programmable data plane to achieve in-network computing. So Marco also had presentations here at earlier meetings. Well, this is the idea that you can implement some application logic, for example, in so slightly more powerful switches. I would say that it's an interesting approach, many interesting opportunities, but the systems that we have seen so far, I think it's fair to say, we're rather point solution that assumed, well, you can basically intercept the packets there, work with the match action logic, and like program the application semantics in languages like P4. This is a fairly limited environment and also has kind of strong assumptions. So security, I guess, would be difficult to do, transport protocols. So I would say it's an interesting starting point, but probably wouldn't really suffice as a general purpose platform for distributed computing. So in this group here, so we think we have like two directions that we have been discussing so far. So we're like coming down from these distributed computing systems in the application layer and trying to see how we can maybe integrate those things with the network. And then the, say, P4X approach, for example, we maybe try to move up the stack and try to see what we can do for applications. So just to give us a handle to kind of talk about a few categories. So here's one example that kind of comes from current work that we have been doing for network computing in a group of, say, ICN folks. So assume you have a kind of a network of nodes that can generally offer compute services. So they could run execution platforms or any kind of platform that could run some functions. So we assume that we would be like agnostic to the specific environment. We just be able to call some functions or to create some state. And of course, you want to be able to leverage specific features, so like a GPU here or a trusted execution environment there. But in general, we assume it could be a heterogeneous system, and so you'd be able to use whatever you need for your application. And so in a distributed application context, there could be something like sessions or like a application in progress that would then perhaps allocate a subset of these nodes. And so these would be like part of one session, and you would then use them to allocate, instantiate functions, but also stateful systems that could, for example, also have side effects, keep state for longer time, and so on. So in a system like this, the assumption is there would be like a distributed system, maybe that's programmed in a program, has certain application requirements, runs dynamically, and the dynamic execution determines so what needs to be allocated, executed, what needs to be transmitted in terms of input parameters and results. So there would be some kind of remote method invocation protocol for invoking functions, so stateless functions or maybe stateful actor member functions. And so in this example here, well, these functions could be very, very lightweight, but also, do significant pieces of work. And as I said, so one function can trigger other function calls and so on. So in that system, it's useful to have information about where those functions are. So if for example, if I have a stateful actor, I want to continue talking to that one. It's also useful to know, so what is the resource utilization situation? So how busy is this server, for example, or how well is it performing right now? Maybe it's actually formally not loaded, but I just figure out it doesn't work so well for me. And it's also good to know, so where are still unallocated resources or nodes that I could maybe integrate into the system at runtime. Okay, so in this system, we distribute this information by some distributed protocol. You could also think about using network mechanisms like the routing system to at least partially help you with that, or to use information that you get from, say, transport protocol, like protocols that tell you, okay, this is perhaps has a longer latency right now, or you have some congestion information in that protocols. Okay, so that's just an example to just give you to have some mind share that we can talk about some mechanisms. So when you do that, first question we could ask, okay, what are these functions anyway? So how fine granular or heavyweight are they? So are we talking about like shifting bits in a register or adding or multiplying? Potentially, but or is it on the other side of the spectrum, like some machine learning application, find faces, identify people, call the police, and get people arrested? Possibly. So I think there's a long, big space in between, and Well, potentially, we would say it could be all of that. Potentially, so obviously not as fine granular as this machine instruction there, but you could say have really long time complex functions or services, as well as stateless functions that just process some data or do some data analytics and give you constant results on some input data. So functions in that system would need data. So where does it come from? Obviously, there would be something like input parameters, so an image to process. There would be something like an operational context, so for a stateful service. There would also be something we think like background data that could be kept in a key value store or some database, which could be modeled as a stateful actor, for example. And you could think about how do you specify or use those parameters? How do you identify the context? So provisions like this must be made. Could be like in the packet or in the message that you convey. Depends a bit on the protocol solution that you design, but also what's a sensible data unit? What these functions typically work on. So pair packet processing, so as in service training perhaps, could be useful, but may not be the ultimate goal in the end. So because there are solutions for that, and when we think about doing something for distributed applications, we think it's more useful to talk about application data units and think about some transport abstraction that allows us to convey these ADUs maybe from one function to the other, for example. And obviously in an internet context or in any context, you have to think about security properties. That means authentication, access control, so these kind of things. Functions sometimes need to be able to do side effects to do something useful. These could be persistent side effects or updates to database states, for example, or could be more temporary effects. So these are also categories that we suggest to look into deeper a little bit. I'm not doing this right now. Then there's often, so in our system design, the question, so what are application semantics in terms of how to actually get data? So is it like a pull abstraction or a push abstraction? So pull would require something like a request response protocol, perhaps. Push is interesting if you want to do some, say, reactive programming, so event-triggered systems. So we think that is all fine. That doesn't have to determine what, say, how the network protocol look like. So we want to be able to map these different application semantics onto a suitable protocol, but doesn't have to mean that the network itself, for example, is always using push or so. So it's easy to say that we want to have a general purpose distributed computing platform, but I think for, say, meaningful applications, you also really have to think about performance. So distributed data analytics.
I just want to let you know that you're pretty much.
Okay, I'm almost done. For distributed data analytics, you could imagine having some pipelines that feed the data into functions, and so each function is depending on the input data that the other function generates. So I mean, this has to be well designed to provide any useful performance. And then things like how can I reuse data in the system, things like caching, and so on. Okay, let me go over this a bit right now. So we have more info on this in the draft. So the question is, what does it mean for Coin? So, I mean, first of all, we are the Internet Research Task Force. So I think in general, we think in general it's healthy to think about open networking environments. So let's not make too many assumptions on how shielded our systems are, how trustworthy the peers are, and so on. So in general, it's a hostile environment where you have to run functions on in generally untrusted systems, and we have to find a way to establish trust, for example, so that your code runs correctly and so on. So heterogeneous system, think security from the beginning, and so on. So one idea that we had is it may seem attractive to categorize the work in different use cases or scenarios, like industrial IoT. But actually, we think that it's actually not that useful, because in this example here, industrial IoT, there are, I guess, like 100 different classes of how network computing could be used. So there is, for example, there could be something like a virtual PLC that runs somewhere. That's just a virtual machine, so not that interesting. But there could be also like distributed data processing or somewhere like real-time control. So we think it's more interesting to really categorize these functional properties and interaction types and these kind of things. So our suggestion for, say, if you did some experimental protocol or something, things to agree on, we think would be the model for human method invocation. Which types of functions are we talking about? What is the programming model? Not so much the different bindings. How do you stripe resources, and how you allocate resources? What is maybe more specific to implementations is the different execution environments, the languages or abstractions for those platforms, and a bunch of other things. And there's a long list of other things that I'm not talking about here. Thank you very much.
For the sake of time, we're not going to have questions, but this is exactly the type of stuff that we would like to have discussed on the mailing list. Thank you very, very much for this, Dirk. And Jörg. Lots of great questions, lots of very good things that we already have a little bit thought about. And yes, we should move the discussion to the list.
Okay.
Thank you so very much. Next up is Adrian. And I have to load your new version, so just give me a second.
Hi.
Where's the other position? Where's all the way? No. I know, I'll just I'll find it from here. You have a new version of this presentation. I'm sorry. Technology works.
Okay, hello everyone. I'm Adrien Vion. I'm a PhD student at Telecom Paris, and I will present you my work, which relies on the service chaining, and I will show you how you can rely on existing network intelligence to build in-network function chain. So in a network where in-network computation is enabled, you will have nodes which, in addition to basic forwarding and routing function, would have also other functions running on top of them, which can be some middle boxing running on a commodity server, or some application functions offloaded to a data plane. But in any case, you will need to be sure to orchestrate your network to be sure that the set of functions are placed on the on your network, and make sure that the wide data flow goes through the wide set of functions to perform more complex functions. So in service function chaining, this is achieved with a central control point called an orchestrator, which has some limitation, since it builds a single point of failure in the networks, has some scalability issue, and is hardly interoperable with legacy device. Moreover, chaining such a function is mainly routing problems. We need to steer data flow through a set of waypoints before reaching the destinations, and we believe that this should be at the network layer, and we propose to augment a classical interior gateway protocol to make it functional. So instead of having a centralized control point which micromanage every flow in your networks and your functions, we propose to instead have autonomous nodes which host network functions, and also have a distributed intelligence to steer traffic through a chain of functions, and to choose to instantiate or delete them. So I will quickly remind how an interior gateway protocol works. You have some gateways which are attached, on which some networks are attached. They exchange some information, and based on that, they build a network view. With this network view, they build a routing table. What we propose is that we can bind a specific prefix to each type of functions make sure that the nodes know where the functions are located. Moreover, if you use some anycast addressings, you are able to match not only a prefix to select the functions, but also to map to use the IGP matrix to select the function instance given data flow as to go through. So instead, if you look at this topology, you have two ping functions running on two different nodes, and if you look at the topological view of the IGP, you have only one node, and each instance of this specific function is represented by a link. And attached to these links, you can attach any metrics that you need to choose the right instance. It could be CPU use, or memory use, or the time it takes to process a packet. And based on that, you will be able to build a chain of functions. For instance, if you take these networks with some classical routers running, which are the blank one, and some routers which also host functions. This augmented routers, which we call enable routers, will announce a specific prefix for any functions they host. For instance, if you consider that the yellow functions is an IDS and the pink one is a firewall, you will have extended network view which is on the right, and based on that, you will be able to route first the first flow, which is the red one, to make sure that it goes through the IDS and then the firewalls. And if you base your metrics, for instance, on the CPU use of the IDS will raise, and if the second flow arrives, it will be routed through the second instance, making some load balancing between the different function instances. So we have built an architecture for our augmented nodes, which we call NAV routers. So you have the control part, which is the distributed MANO on the right, and which receive a high-level policy, such as the mapping of a specific function to an unicast prefix, and which will constantly monitor the different function it hosts, and based on that, compute the metrics it will announce through the IGP to make the other routers aware that it hosts the functions and what is its current use. The second logical part will take the VNF routing algorithm, will take the augmented view shared on the IGP, use a path computation algorithm, and build a function service table which will map the location of the functions and push it through the connector, which is the part which will link the IP networks and the functions. And based on the encapsulations that we have used, which is NSH, which have been normalized at the IETF, you will be able to map the next function to which with the locations your packet has to go through. So we make a simple implementation of these routers. The virtual network functions are simply functions in a network namespace. We build our connector with P4 to make it. We didn't use OpenVSwitch because it didn't have a stateful memory. So we use P4 to implement our connector to make sure that each flow will be processed by the same instance. We make flow routing and not packet-based routings. And we used an open source stack, which is FR routing, as for our router, which runs OSPF. So we have made some large-scale experiments with this implementation. We package our NAV routers as LXT containers, and we emulated 87 node topologies, which is the NISP inferred topology made by the Rocketful project. And on top of these topologies, we deployed 10 virtual network functions, and we ask and we configure our network to make sure that it goes through first function, which is the yellow one, and the second, which would be the pink. There is a 5 instance of each type of virtual network functions, and the routing policy is the shortest path, and each NAV routers take obey up routing the decision. And what we show is that based on the link state advertisement update frequency, you are able to have a stable load balancing on the different VNF instances running on our NAV routers. So what we did achieve is that we have a fully distributed framework to chain in-network functions, which is not only interoperable with current routing system, and which brings resilience and scalability, since the IGP is a field-proven routing protocol. And we achieved to balance the load among the different virtual network function instance, and we don't have to add any configuration when we add a new virtual network function instance, since when a NAV router choose to start a new instance, it just have to announce the unicast prefix related to this to the VNF it has instantiated to make the routing system aware of the new resource in the networks. And in future work, we would like to see if we can extend our proposal to inter-domain service provisioning using BGP. And to study the different metrics which could be used to take routing decision for the virtual service functions. Moreover, some classical IGP maintenance and failure techniques could be applied to our solutions. And what the next step of our works will be to check if, based on the augmented topology we build, the NFV routers would be able to take autonomous decision to choose to start or stop an instance based on the load on the networks. So if you have any question.
Please state your name. And,
Just answer.
Okay.
So I was surprised to see OSPF used here. Mixing reachability and policy in single protocols is a bad idea in general. There are reasonably stable work called BGP for NSH that's progressing in best working group in IETF. And it has, BGP has built-in constructs, so route targets, import and export to impose policies. So it would have been much easier to implement, and inter-domain would work just as is. So maybe something to consider.
Okay, thanks.
Doug Montgomery, so do you have the ability to choose your route based upon the overall complete service chain as opposed to an incremental series of shorter stop decisions?
What we have done for now is to take up-by-up decision running the shortest path algorithm. Nonetheless, if you have the augmented view, you can use, in my opinion, any path computation algorithm to take a more complex decision if needed. And you could also, instead of make up-by-up routing, make source routing using, for instance, SRv6 to SRv6 to do that.
this will be our last question.
Diego Lopez, would you mention this VNF provisioning? It's in general orchestration, I guess, and the life cycle and all. How do you control the life cycle when associated with the routing?
For now on, we consider only virtual network functions which have started, and we do not deal with the life cycle.
Static. So you mentioned this about the balancing is for the initial setup.
Yeah, but if you start, we have in our first paper, we have made some experiment for load balancing scenario where you have, for instance, two virtual network function run at first, and you choose to start a third one to change the balance between the virtual network function instances. So it is possible to modify the traffic engineering doing that.
But then when you make the decision to scale out,
this is an open question. We do not have covered that.
I was curious how this was propagated through the routing updates. Well,
okay.
Interesting.
Thanks.
Thank you very much. Thank you.
Does everybody sign the blue sheet? Where is the blue sheet? We have one. There's another one out there somewhere. Anybody need it?
Yeah, I can see it. mean, I could start with our
Yeah,
slides
just
already.
start and it's going to, the slides are going to appear by time.
Okay, so hello, my name is Ike, and I'm here to present our draft on the industrial use cases. What you will sometimes see behind me. Okay, so there are. So what you'll see here, that's actually what we are working on right now with mechanical engineers in Aachen. So the industrial Internet of Things. As you can see, there are quite a lot of different robots working, a lot of sensors measuring something, and everything is now more and more connected. And what the mechanical engineers tell us is that they want to essentially move all the data that they collect there into edge or remote clouds. They will also want to control the different robots also from the clouds. And yeah, essentially as a third aspect, all the data that they move to the cloud, they want to use that and actually throw machine learning and data mining on it to later to use to find out how they can improve their production environment and then feed that information back into the system to make it better. And based on these three aspects that we've seen here, we've then taken a look at how we can improve that with in-network computing. And you can see here the general abstraction from the previous figure, namely that we have sensors, that we have actuators on the left-hand side. So one end of the communication there. On the right side, you see the edge clouds and the remote clouds, which will then be the other end of the communication. And in the middle, we have the network. And what we now propose is that we could place certain functions within the network to complement their use cases that they want to achieve. And there, Klaus has presented in Prague, and there we have proposed two of them already, so network control and traffic filters. And we are now also proposing data stream processing as well as industrial safety aspects. So as these two use cases were already presented in Prague, I will only go shortly over them. So network control, the general idea is that the different robots are now controlled from an edge or a remote cloud. And here the problem is that the latency that is induced by the network is too high, so that the control loop cannot really be working anymore. And what we now want to do is we want to push simplified versions of the control algorithms already within the network, so that there can be short answers maybe to signify to the actuators that everything is working okay, and so that everything is still working. On the other hand, we have traffic filters. As more and more sensor data is there, the amount of traffic that needs to be pushed into the cloud is getting larger and larger. But a lot of sensors cannot really be configured well, so there might be redundancy in them, and so not all the data might be necessary to push to the cloud. And we simply want to filter out unnecessary data already then within the network to reduce the load on the network. The third aspect then, which is actually quite similar to traffic filtering, and in Prague we presented them as one, is data stream pre-processing. So the different sensor values that are pushed into the cloud are oftentimes then simply combined to form new values, and then the mechanical engineers only want to store those combined values. And if we now can achieve this combination already within the network, we wouldn't need to push all the data into the cloud, but only the combined values. So this would then again reduce the amount of data that needs to be pushed to the cloud. And then as a fourth aspect, we think about complementing the current safety measures that are there in the production domain. So typically you have like laser barriers so that machines stop when someone goes through them. But nowadays the production environment gets more and more dynamic, so that even production or working stations move around in the production hall, so that it's now not that easy to build hardware solutions for that. And we now propose to complement that by utilizing data that is already being sent to the cloud, for example, camera data. And we could, for example, identify if one camera sees a robot moving in this direction and the other camera sees a robot moving in that, a human moving in the other direction, and maybe identify a collision course that then the robot could be signal that it should stop. So in the draft, we then proposed quite a lot of research questions for all the 4 different use cases, and I've tried to condense them here into 2 categories. The first one is the design and development of the network functions that we want to do. So here the question is how we can account for the limited computational capabilities of the network devices. So we cannot, so for example, in the control scenario, you typically have quite complex control loops and control algorithms, and so it's the simplified versions of them might introduce some sort of inaccuracy, and we have to account for that as well. And then as the second aspect, so now we can build them, the different network functions. It might be a good idea to find out how we can, for example, provide basic building blocks for the functions so that they can then be easier combined, or new network functions can be built easier. The second big point is then the operation and the deployment of the network functions. So now we have the functions, but how do we place them? Where do we place them, and how do we coordinate them? So for example, if we have 2 functions in the network and we replace the first one, how does that affect the second one, for example? And as a second aspect, we then also see that these network functions will certainly affect the functions that are then computed at the applications in the end. And here we have to consider how this will then, how we can define the interaction between the network functions and the applications. So what is then next for us? We plan on updating this our use case draft, and then we especially want to do another draft, or we plan on doing another draft on transport protocol issues. So this was then basically what I stated last on the slide before. So the interaction between the end hosts and the network functions in the middle, because if we simply for example, combine the two sensoric values into a third one, and then only one packet still survives. Maybe this violates kind of the end-to-end principle, and we want to elaborate on what we think might be the problems here, and we want to find out what we could do about that, or what essential requirements for such a protocol would be. But I want to say that we don't plan on designing a protocol here. We simply want to elaborate on the challenges that we have there. And if you're also interested in that, we are very looking forward to collaboration in this regard. And so then contact me. Thank you.
Are there any questions? I actually have one, without my chair. I should have gotten a hat. I think there's a lot of very good opportunities in what you mentioned, but I read the draft also. I think what is missing is making a strong differentiation of what is already existing in automated industrial environments, which, as you know, are pretty advanced, and what you're bringing with this architecture. And I don't think it's clear in the draft, and I don't think it's clear in the presentation either. Because if I look at this with a very cynical hat on, I would say, they already do that in highly automated production. But I actually know from other stuff that there are use cases and there are places in industrial environments where this type of work, that your suggestion, has a lot of room. So I would suggest that in the next version of your draft, that you clearly identify What is the difference between what your suggestion and what is currently happening in automation?
Yeah, thanks. That's a nice suggestion. We will definitely think about that.
Hi. Have you reviewed existing transport protocols? Is anything missing? Why do you need additional draft? What's missing in current variety of transport protocols?
Sorry, I didn't get that from the acoustics. Could you repeat it, please?
Your next step is draft on transport protocol.
Yeah.
Do you need something new? Is there anything missing in existing transport protocols?
So what I basically meant with that is this violation of the end-to-end principle. So we don't think that it will work with the existing protocols, or at least not out of the box. So the end hosts somehow have to know that someone in the middle is interfering with what they are doing, and this is actually what I meant with this draft on the transport protocol.
So it sounds like AMQP like protocols that's usually used in this kind of environments.
Sorry?
AMQP. So, there's a broker in between. It's not end-to-end.
I didn't get that either.
I'll talk to you later.
Okay, thank you. Okay. Thanks.
Has everybody signed the blue sheets? If not, they're in the front. So raise your hand. Raise your hand. Okay, thank you.
All right.
Take it out there.
No, this is good. Okay, thank you. All right. So can everyone hear me? Okay. So I'm Jingchen Jiang. I'm an assistant professor at University of Chicago. This is actually the first time I'm in IETF, and it's very happy to be here to share my research. And hopefully at the end, I can connect my research to the agenda of Coinrg. So unless you live on like in a rock, you know that video analytics is everywhere, right? From public transportation to public safety, everything. But the real research challenge in terms of networking and systems is how do you build a network system to support the video analytics at such massive scales? Okay, and let's first look at some trends here. So, is this going to be aligned? Oh, okay, great. Okay, so first of all, there are two trends in video analytics. One, these neural network models are getting more and more accurate at the cost of more and more computing resource. Okay, so it's getting more and more expensive to run these models. And second, there's just a lot more cameras. So these two trends has led to this dramatic growth of the cost in video analytics. Okay, now just to put that into perspective, this is not just about compute storage; it's also about networking. Okay. Now, to put that into perspective, think about video streaming, internet streaming videos like Netflix or YouTube, right? These are the kind of applications that account for 80% of the internet traffic to consumers. Now, imagine all the network systems these days, like CDNs or cloud, they're all built around these traditional applications. Now, the fact is, at least surveillance cameras videos have already exceeded the traffic of internet streaming video. And the fact that these cameras, analyzing one camera feed is way more expensive than just streaming one. Okay, so that means there is the current today's internet systems is way less than what's needed to analyze all these video feeds. Okay, so clearly there's something needed to increase the accuracy of these analytics with low cost, and do so in a way that can scale to the sheer number of cameras and the video feeds. Okay. Now, just to give you a sense of what video analytics systems look like, you have a camera capturing video, and the video can be analyzed locally or can be sent to the server for further analytics. Okay. So naturally, you can imagine there's a kind of edge to cloud continuum where the high resolution videos will be analyzed locally, okay? And then only the part of the video that needs further investigation will be sent upstream to some more complex model, typically running on an edge cluster, Okay, and then it will do some further filtering, and the remaining video will be only the remaining video will be sent back upstream to a very complex model in the cloud. Okay, so now so far all I have talked about is very similar to everything you have seen in edge computing, right? But there are actually two unique properties of video analytics. The first property is that the video pipelines must be very adaptive to the real-time video content. Now, in a jest, what that means is when the video content changed over time, right, the resource demand for these video analytics pipelines will vary dramatically over time as well. That makes resource provision very challenging. Okay, so let's just recap. The challenge of video analytics is to balance accuracy and cost. Okay, so prior work, I mean, all work these days have been trying to do is to kind of customize the video pipeline to the video content. So why this is possible? Well, imagine this is one of the very typical video analytics pipelines out there, right? And there are not a lot of knobs, configuration knobs that you can tune. So the frames of a video gets fed into this module in the middle that resizes the video and then select which frames to sample, and then it will get fed into this neural network object detection software. Okay, so you can see there are a bunch of knobs you can tune, right? So you can tune the resolution, the frame rate, and even which neural network object detection model to use. Okay, so so people have been trying to exploiting this kind of these knobs to customize the pipeline to the video content. Now, I was just informed that this video is not going to play, so I'm going to just ask you to imagine what's going to happen here. Okay, so let's say this is actually two same video. On the left-hand side, you see these bounding boxes. These are boxes detected, cars detected by the neural network. And if I play the video, you will see these cars are going to be staying put. I mean, they are stopping there. And so if you use low frame rate on the left versus high frame rate on the right, their accuracy will be pretty similar. Okay, so when the object is pretty static, low frame rate obviously will be enough. There's not much going on. But if you if I were to click the play button again, right, you will see there are cars moving into the picture and running in high speed. And if you have objects moving at high speed, the low frame rate will give very low accuracy because it will lose track of these objects. Okay, so what it means is, that gives us a key insight. That is, the video analytics pipeline must be customized to the video content, the real-time video content. So basically, as the video content varies over time, for example, speed changes, right? The best configuration will vary over time as well. Now, this is not just about frame rate. I'm just using frame rate as one example. Resolution and the underlying neural network classifier should also be changed depending on how frequent the content changes. Now, all prior work has been doing is so-called one-time profiling. They profile the video up front and then stick to the configuration they think is the best through the remaining of the video. What we're proposing in this recent work is try to argue that instead of just using one configuration that seems to be good, we should adapt the video pipeline, okay, over time to the dynamic video content. Okay, so this is the new idea. We studied this idea in a recent paper. So what is mean architecturally? Okay, so what it means is you're going to have this controller in the middle that's basically sitting in this continuous loop, right? It will periodically update, profile the video and update the control knobs you use, like what frame rate or what model you should use. Okay, and it's going to run this continuously. So I'm going to skip a lot of details here, but the upshot is you can kind of achieve a lot of resource saving or a lot of accuracy improvement, right? So this is one traffic video data set, and you can see on this, the blue ones are profiling just once up front. Okay, you don't change the configuration, and the red ones is the proposed method. You're continuously reprofiling and updating the configuration, and it made us be able to claim this like higher accuracy at the same cost, or you can achieve the same cost at a very small fraction of the accuracy at a very small fraction of the computing cost. Okay. Now, this is just research, but what it tells us is even this is good news, this actually makes the resource allocation very challenging, right? Because now whenever the content changes, you have to change your resource allocation. And this is actually the plot of the resource demand of this system over time, okay? And you can see the resource consumption kind of changes by 5 to 20x, even just in a few seconds, just because the content changes rapidly, right? And this basically raises the challenge, how do you actually do resource allocation in network computing, right, to cope with this kind of a spiky workload? Okay, so that's one takeaway from the first part of the research. Now, for the remaining couple of minutes, I will be just briefly talk about the second unique challenge, unique property of video analytics. Oh, only half. Yes, exactly. Okay, so what that means is, okay, so let's imagine, again, you have a network connecting a camera and a cloud. And the camera doesn't have local resource to process the video, typically, right? So the video has to be streamed out to the server. Now, what traditionally what people do is they're going to look at the video and just compress it to some quality level and then send the video back to the server. This has two problems. Either you encode the video in too low quality, it loses accuracy. You can't see anything. Or you send it in high quality, it's good for accuracy, but you may not have enough bandwidth to send it, right? Now, the fundamental reason for this, actually, is because this product, the traditional video streaming protocol makes sense not to use the feedback from the user, because for traditional video, the users are actually human beings, right? You can't ask them to give you experience feedback. But in video analytics, actually you can, because the consumer, the user here, are actually logic. It's an algorithm, right? You can actually pull some feedback from it. And this is what we do. This is what we're trying to do, and this animation got messed up. But what's basically happening here is you can kind of just send a very low quality version of the video to the server, and the server will run some analytics to give hint to the client what it actually needs, right? Real-time hint. So that's another, that's kind of a new way to do this video streaming for video analytics, okay? And this can actually save a lot of bandwidth, but still achieve the same high accuracy, okay? So the takeaway from this talk, just two takeaways from this talk. One is that the video pipeline must be adaptive to the real-time video content, okay? And that means whenever the content changes, right, the resource demand may vary as well. And that will cause some very spiky workload. And whatever in-network resource allocation or network allocation, resource allocation mechanism we're proposing must be able to cope with that, okay? And the second, because we are dealing with, this video analytics is dealing with some algorithm as the final consumer of the system, right? You can actually leverage some of this real-time feedback from it. And this actually opens up new opportunities to bring the goals of these analytics to the resource allocation control loop, okay? And thank you. Ready for questions. Thank you.
Any question?
Oh, thank you.
So I guess I'd love for you to elaborate on what you imagine it would entail to bring the analytics goals to the control loop. Do you see that there is metadata specific to these kinds of cascades that could be exposed? And then, can you say more, given that you're the sort of area expert around this?
Yeah, good question. So the question is if you want to leverage the server or the analytics logic feedback, right? So it will be better to have kind of a standardized version of it, or metadata to generalize most kind of feedback that will be useful. So I think this is very much in the early stage of research. There has been several papers along this line. One thing that's really interesting is so-called you make some assumptions about what the content or the video, the dynamics of the video would look like. So basically you let the server see something, okay, and the server will tell you, okay, so is this anomaly? Is this usual or not. If it's very unusual, right, so it will ask you for more information. So for example, if it looking at very low quality video, it sees these objects that just appears once and disappear all of a sudden, that doesn't make a lot of sense, right? So that's kind of anomaly is one thing that's really stand out across several papers. I'm just trying to really generalize that. I mean, obviously they have very different mechanisms to solve that, but anomaly in the result is one interesting result, interesting thing to look at. The other thing is so-called confidence. So confidence as in, so these neural network usually have some scores attached to each detection. And scores being high means it's very confident that this is actually a thing. If it's low, that means I mean, mathematically it doesn't mean anything, but you can treat it as it's not being very confident. Okay, so that score is one thing also useful as a feedback for you to pull more useful information from the edge. Okay.
Thanks.
Yes.
So, Emil from Orange, do you know if it changed a lot the bit rate or is going to be much more variable, or do you still have a pipeline with a constant bit rate?
If you do this, the bit rate will be changing a lot versus pretty stable.
Okay.
Right. Yes. So, like I said, it's very content dependent. If you have a big object in the middle, right? If self-driving car, if your car is staying stop in front of you, low resolution will be good enough.
I understand that, but do you have some figure about it? Is it
No,
1 to 10,
not here.
1 to 100 or 1 to 1,000?
No, definitely not at the scale of like two orders of magnitude. It's usually within 1 order of magnitude. Okay, so like if you talk about video, you're changing resolution and QP, right? Quantization parameter.
No.
That's usually within a range of certain value. I mean, low and high won't have a difference of more than 10x. Now, that has a reason. That has an actual underlying reason that it's because the neural network these days assumes certain input size. So even if you give a very, very high resolution video, it will resize into something smaller as well. So I'm just saying the magnitude of resolution changing that I'm seeing is not really the full scale of variance that you will be seeing if you have better neural network. Does that make sense?
I have another question. Does it reduce the number of steps or tasks in the cloud to edge path?
Steps as in?
So you were describing that currently there are a lot of different steps to extract the analytics.
Mm-hmm.
And do you have an idea about the number of steps that is going to decrease?
Yeah, that's a good question. I think
it's about scalability.
That's actually a very good research question. That's actually a very good research question. I think most of the work in this space is not trying to figure out the optimal number of layers between the camera and the cloud. They're trying to say, if you have this number of layers, how do I lay out? I mean, how do I spread the analytics across these layers? I think that's actually a real good question from this group's perspective to investigate.
Thank you so much.
Okay.
Yunchen, Dave Oran. Could you put up the spiky load graph again? So I'm trying to read the x-axis is kind of compressed. So how much time is between the bottom and any given peak? Is that seconds, tenths of seconds? I can't really see this.
This is 10 seconds.
Yeah, well, let me sort of really get to the question I want to ask. Mm-hmm. How many RTTs do I have before I see the spike? Before I know that spike is big?
Good question. So this is, at the scale, time scale of seconds, granularity of seconds. So I think if you look, if you're talking about network with RTT, sub-second RTT, right? In theory, you can catch that right.
That's what I'm trying to figure out is how can I catch that and get the resource allocation done?
Right. But I'm just saying, in theory, you can catch it right up front, but you do need several iterations to like really converge. And add to that, resource allocation is not free, right? So it's not instantaneous. So you kind of need to take that into account too. Maybe that's actually what's taking most of the time.
And then, given that edge resources are constrained not just in compute but in memory.
Yes.
The question is, can I buffer enough of this peak so that I can keep the data long enough till I can get the resource allocated?
I think you're right when you said memory is the bottleneck, because usually this neural network is what's consuming most of the memory. I think if you just want to buffer the video before it's actually analyzed, yes, I think you should be able to buffer those videos.
Okay, so you're saying that the size of the video is small compared to the size of the model that you need at the edge.
Yes, actually yes.
Okay, well then, the interesting question is, do you need the model everywhere, and can you get the model in?
Right. Yeah. I guess that's the next question. If you don't have the model, I guess the memory will be the bottleneck for buffering the video. But I think these cameras usually have pretty large storage and buffering.
Super. Thank you.
Thank you.
Last question.
Yes. Did you consider how?
Can you state your name, please?
Yes, Sharon from Nexar. Did you consider how urgent is it to understand what the camera sees? Like, if it's really urgent, then the neural network should be on the camera. And then if it doesn't understand, then only frames, on-demand frames, not the whole video, because it can't. It's too much.
So I think you're definitely right. There are two extreme of the system, two extreme versions of the views, right? So you can have like self-driving cars, where you do have a lot of resource. I mean, it's a car, right? And everything is very must be very super real time. Right. So in those kind of situations, you do want everything local, versus if you have a bunch of surveillance cameras or a camera network where you have like thousands of cameras, much cheaper than the one you have on self-driving cars. And then in those kind of situations, you need to have a back-end network system to analyze the data. But actually, you're right. In those cases, most of people are assuming they are not as real time as self-driving cars, so they can tolerate certain level of delay.
Yes.
Okay. So, but you're right. Maybe in the worst case of, the worst version of both worlds, right? You have a lot of cameras, cheap ones, and you need super real time reaction. That's the kind of holy grail of this kind of systems.
No, but I agree with you. There has to be layering, because the car itself is always going to have some kind of limitation versus. So, but what you can consider is a neural net on the camera. Especially if it's a moving camera, you cannot expect what's going to happen. Somebody may jump, the kid, the ball, and then in the edge, if you need sub 10 milliseconds, and then in the cloud, if you need sub-seconds, something like that.
That's true. Yes, there's a kind of hierarchy of delays you can tolerate if you want to go a further layer up front. Yeah. Thank you.
Thank you very much. So the next presentation is is remote. So can Jesper, who's actually called Mark Leclerc, I think you're the one who controls the microphone.
Okay, yeah. Maria Jose, can you hear me okay?
We hear you great.
Very good. Okay. Let me see, do I control the slides?
I can control them.
Okay, very good. Okay, so let's start. So my name is Jesper Eriksson, and I'm a VP of Product Management, the co-founder of Noviflow. And I have logged on to this session using Mark Leclerc's registration credentials. He's a dear colleague of mine, VP of Marketing and Strategy, and also co-founder. And to do this, I had to promise him not to use any coarse language or get him into any trouble whatsoever. So you see Mark, but it's really Jesper Eriksson. So on the first slide, this presentation is really about the evolution of SDN from OpenFlow to P4 and P4 runtime. And the slide that you're looking at right now is just an introductory slide. Noviflow as a company, we were founded in 2012 as a pure SDN company. We really released our first commercial OpenFlow 1.3 switch in second quarter 2013. And our core technology is really this programmable match action pipeline using Mellanox MPUs and also Barefoot Tofino. The key verticals that we operate in and where our technology is used is cybersecurity, different types of gateways, and then also on-demand bandwidth solutions in WANs and broadband access. So please change. So what is a match action pipeline? Well, so the match action pipeline resides in the switch silicon inside the switch or router, and it's really the embodiment of the rules by which we want to process the packet as it goes through the switch. And in most switches, you'll find a fixed ASIC, and that's really what you see on the left. And in a fixed ASIC, you'll find a fixed set of match action tables defined in the silicon. The size of these tables is fixed. What the fields that you can match on is predefined, and the actions that you take in the table, in that particular table, is also fixed. And then, you know, as an application programmer trying to use this in an SDN context, you know, I would have to try and map my application into this fixed match action pipeline. So it's really a what we call a bottoms-up programming paradigm. You have to see what's in the silicon, and that really drives what you can do with your application. And then on the right, you see a programmable silicon, and here there's no prior set of match action tables defined in the silicon. And the application programmer creates the pipeline to specifically meet the needs of the application. You know, the programmer from scratch says, I need this many tables. This is the size of the various size of the tables, the types of the tables, and then what match fields and actions I want to use in each table. And it really allows the programmer and the application to drive the packet processing pipeline in the silicon. Okay, next slide, please. So who cares? You know, why is this important? Well, in our view, you know, this programmable match action pipeline enables the following thing. The first one is faster introduction of new network functionality and protocols. And, you know, there are an endless list of this. I mentioned a couple here, you know, IPv6, VXLAN, SRv6. Essentially, any new protocol that's introduced, unless the silicon is programmable, you have to wait for the next generation of silicon to be able to introduce that functionality. It also allows you to do fast prototyping of new capabilities because the functionality is software defined. Another key point is that this allows disaggregation of network hardware and software. The hardware looks more like a server and then can be sourced differently, you know, and then the software is really what defines what the functionality is. And then the third bullet here is features are defined in the software and not in the hardware. And what that drives is there's really no forced obsolescence of the networking equipment, as you can upgrade the functionality through software. And over time, you can also repurpose the network equipment by changing the software, more like a server. So that, yeah. And then we go to the open flow, starting with the open flow match action pipeline. So and this is like 1.3, 1.4, etc. And it allows you to define any number of tables or steps. And in any one of these tables, you can match on any combination of a predefined set of match fields and then operate on the packets using any of a predefined set of instructions and actions. So it has a lot of freedom. The programmer can say, I want 2 tables. I want to match on this in the first table. I want to match on this in the second table. I want to highlight the metadata field as an interesting feature in OpenFlow and also in P4. It allows you to bring the result from one table to the next and match on it. It's like a carry forward variable. And we have one customer that's using this to progressively build the result in a number of tables, and then in the last table match on the overall result of what happened or what the pipeline calculated. Okay, next slide, please. So here you see a real implementation of a true OpenFlow switch. And the purpose of this slide is really to illustrate what a true OpenFlow switch looks like. And a switch that's compliant with OpenFlow 1.4. And it may give you some ideas of what you can do with OpenFlow and from a network computing perspective. And what it shows is it defines, let me see, it's hard to read here. Yeah, so it allows the programmer to create a pipeline with up to 41 different match fields as defined in OpenFlow 1.4, up to 6 instructions, and up to 56 actions. And actions include the ability to change the value in any match field. And you can put any match field and actions instructions in any table, and the tables may be a wildcard table where you have don't care bits in the match field, or an exact match table. And then each table, the width or the number of match fields that is defined by the programmer, and the number of rows is also defined by the programmer. So a good example here is the NoviFlow implementation, where you have up to 1 million flow entries in a TCAM in up to 60 different tables. And then in the exact match use case, you have up to 6 million rows or flow entries in up to 60 tables. So the application programmer can really put together the pipeline using these primitives that then supports the application. Yeah, so move on to the next one, which is the P4 the P4 and P4 runtime match action pipeline. So NoviFlow, we've been working with P4 for about 2 years. We released our first commercial product in May 2018. This was a switch NOS that allowed you to use the Barefoot Tofino switch as an OpenFlow 1.5 switch. We essentially wrapped OpenFlow around P4 and allowed a user to create and run an OpenFlow pipeline on a Tofino white box. So basically, the user saw an OpenFlow switch, but internally in the NOS, we mapped that into P4 code that got compiled and pushed into the silicon. So that was like the first step. And so when you look at the P4 runtime match action pipeline, the P4 part is the programming language that is used to define how a switch silicon process the packets. You can define the parser, which is what kind of match fields you're going to get. You can program the actions. What am I going to do? And then I can program and define a match action pipeline, tables in a match action pipeline. And then the P4 runtime is really the interface from an external P4 controller or internal P4 controller to access and program this match action pipeline. Add flow entries or initially what you do first is you load the compiled P4 program, then you can add, delete flow entries in the match action tables, you can collect statistics. So the P4 runtime is really the comparison to OpenFlow from a networking perspective.
About a minute and a half. And
okay.
Also, while I'm talking, your slides are copyright. I saw that when you started. That means I will have to take them out of our repository. Is that okay with you? Because we don't have it. We cannot have copyrighted material.
Oh, okay. So what I can do, Maria-Jose, I could submit another one without the copyright. Let me check with Mark on that. Yeah.
So you have about a minute and a half.
Oh, okay. Very good. Okay, next slide, please. So this slide is really to illustrate the extent by which this the parser and the match action pipeline and the actions are defined in software. So you basically define an Ethernet header, an IPv4 header, the tables, what you match on, what the actions are. And so it's the software definition is driven all the way down to bare bones. And then so you have a header types, parsers, tables, actions, metadata, and then you have this thing called external objects. So it allows you to create functions in your pipeline that will do operations like checksum, registers, counters, meters, and also any other thing you can think of. So move on. Next slide. So comparing OpenFlow and P4 runtime, both of them give you a programmable match action pipeline. However, P4 runtime gives you additional freedoms as you can program the parser and also define your own actions. In OpenFlow, you could do some of that through experimental extensions, where the developer could define new match fields and actions. So next slide. So here's a slide showing the components of a NOS, and what we've been talking about is the OpenFlow and the P4 runtime and that part. But on top of that, in a typical NOS, you also have configuration management, operations management, security management, and other extensibilities. So that was really my presentation. Thank you.
Thank you very much. Are there any questions?
So I have a question I have asked
Dave Oren.
Oh, Dave Oren, yeah. P4 people multiple times, and I'm curious if you have potentially a more satisfying answer to this question, which is, I have two programmers, each of which have written a P4 program, and they don't know about each other. What's the composition model for composing two P4 programs into one? And what's the model for how those two programs can be loaded onto the same switch? And what's the model for if I want to change the program of the switch without resetting the switch?
Yeah, those are very good questions, and I'm afraid I don't have the answers to that right now. But I can follow up with that.
I don't have the answer, or the answer is the P4 people have no clue how to do this.
It's more I don't have the answer. So,
Okay,
but I can get back to you with the answers on that.
Yeah, if you can send that to the list, that would be great. And by the way, for those who got here very late, Jasper and friends lent us two engineers that probably could have the answer to your question. And so that was really great. Are there any other questions? At the hackathon, yes. And the code you saw was similar to the stuff we did at the hackathon. Any other questions? Thank you so much, Jasper.
Yep, thanks. Bye-bye.
I know your slides are there, so it's easier. We can get it.
Good, thanks. Good, very good. There's a thingy somewhere. Great. Good, thank you. I'm trying to be timely. So this draft is submitted a couple of weeks ago as a result of ongoing work as well as proposed research. So a lot of the questions we are asking, we have ideas of answers, but not real ones, really. And that's why we thought it might be a good idea to actually put this to the proposed research group, because we feel that might be a good space for it. The work is largely centered around microservices. That's what we're working in. But we have a slant in the draft around what we call app-centric microservices. And the reason for that is really to start from the app economy in the smartphone world and look at smartphones. I have about 200 on my smartphone. And it has driven, the development of mobile experience as we largely know it. We use applications on our smart devices. The design is fairly static. They're software modules. They're packaged into an application. You download them from a Play Store and you're done with. There are extended client-server interactions you usually see within these apps, but that's about it. And what we want to move to mentally, at least as a thought experiment, and we have first demos on this, is to mental model where we look at an app as a collection of microservices that you can decompose and start bouncing around in the network. And that's why we call it app-centric one. So you decompose an app into a set of microservices, you execute them on one or more distributed resources that can be at the edge of the network, in the cloud, wherever they are. And you interpret each of these compute resources as a pico micro data center. And that's how we term the name App Center. So we don't look at the data center. We said, well, you just run micro apps on it. Right, that's where it comes from. The use case we've demonstrated and which is described in the draft is mobile function offloading. So this runs on standard Android. We do Android because we just don't program iOS for reasons of resources, really. We wrap helper classes, microservice helper classes, around modules, and this is done purely at design time. So you have to do this at the moment, at least. We're also working on a runtime version that does this automatically. And the example that's described in the draft is, have a very simple. You receive an image, you process the image, you do some very snapshotty kind of thingy, and you display it. 3 microservices makes a lot of sense, right? And now you interpret a given experience like watching that morph video as a chain of microservices, receive, process, display, and you're done with. And when you run the actual application now, which is still an application, it's being installed as an application from the actual Play Store, and all these microservices run on your device. It's just as you're used to because it's an app, right? But what you can do, we wrote a small little software module that kills the modules on the, it essentially kills the processes. And what you see, because they're microservices, they bounce off the actual device and run in the network as in-network computing. And in the draft, we describe, apologies for using the actual ASCII figure. I should have probably used a better one. And we realized that over an SDN infrastructure, the app, if it runs, so DPR on the top just stands for the modules, display, process, and receive. You run them like that. They run on that's just the app as you see. Everything runs on your mobile. And we have a very simple control UI, no intelligence in there. The intelligence is yourself that knocks them off. And you kill, for instance, the processing, the P, one of the microservices in the chain is missing, and it jumps onto a processing server in the network. The processing is more capable, so you can run different processing routines, etc. You kill the D, and it jumps onto a smart TV, which only implements the D function, not the other ones, because it doesn't do processing. So you get distributed experiences. Really cute. We ran this as a demo, as a concept demo in February this year, as it works with standard Android. What we describe in the draft is what are some of the technologies you can do this all as a vertically integrated demo. Works perfectly. The whole point about standards is to do this obviously in a way that it works not just for our demo, but it works for everybody, right? So we outlined certain areas in the draft that we feel work needs to be done. Some has to do with application packaging. Not entirely sure that's an IETF area, but we nonetheless describe that, which is usually done at design time. And what we do, we define wrapper classes, we expose those. We are in the process of injecting them into the open source community so they can be used. You can also do profiling to do this actually at runtime. That's the real fun part. So you have an application that hasn't been designed as a microservice, and it's being pulled apart into microservices at runtime, and then it starts bouncing about in the network. That's actually quite cool. We hope to demonstrate that in a couple of months' time. Another area is service deployment. How does the P server makes it there? We remember the one before, so there was a processing server in the network. We actually have done this by combining application installation with service orchestration. When you install the app, we are not using the actual Android application installer. We do use, but we have an extended version which not only installs the application, but it pulls out of the asset package of the application package a service orchestration template and pushes it into the network and says, dude, I need a processing server. Can you please install one for me, right? And the package is over there. Again, there's a lot of standardization you would need to do to make that work outside a vertically integrated demo. And the integration with the app installation model is really quite cute because users just see an application installation. They don't really see a service deployment. So that's one of the reasons why we like that. Service routing. I talk about stuff bouncing about. Now, obviously, that requires that you have in place a service routing infrastructure. It's usually done as a combination of DNS and IP routing. Our bouncing about is relatively flexible, so we use ongoing work in the SFC working group, which is now going through the ISE route on so-called named service function chaining, as well as service routing over L2 environments that allows you to actually do this really flexibly. So we have a couple of demos where you will see if you do this in a standard DNS plus IP system, it won't really quite work because the dynamicity is not there. And we described this issue in the draft as well, the dynamicity of in-network computing, in particular, when you bounce functions around based on user interactions. I walk into the room, I suddenly want to go from my actual display on the mobile, I want to jump onto the display in the room. That's very, very flexible. And it requires solutions for service routing that are probably different from the ones we know. Service pinning, we described that based on the use case. If you have two resources that actually implement the same microservice, how do I make sure I'm actually using the one that I really want to use? Think about the display. It might matter an awful lot on which display you actually display stuff. Even though it's the same D microservice, I really want to have that one. I don't want to have the other one for various reasons. The pinned relations can change very frequently. Your requirements, your constraints change. I might walk in a different room. I do want to go use actually the other display. So the pinning has to change frequently as well, right? And how do I do this in a standardized manner that will allow me to do this? And the last area that we describe is state synchronization. We do work with a mixture of stateless as well as stateful microservices. You can't enforce only one of them. And therefore, state synchronization is very, very crucial. Typical use cases that are very, very stateful are, in particular, gaming use cases, where you indeed need good state synchronization. So these are the areas. And I said we have a couple, there are references in the draft you can see to ongoing work that we also are currently doing in the IETF and other working groups. But generally, we try to keep those sections as these are cool areas to work on. I think we need some work in this in order to, as I said, move into standardized environments. And it would be good to have a place for this, right? So the conclusion really is, really trying to stick to my 10 minutes, is that the draft positions an evolution, and we try to stick this to the app model because everybody knows that. Actually, we played this story to, in particular, people who don't really quite understand what the internet really is with the sense of IP packets. We played this to teenagers, and they loved this story. Right? For them, the internet are application installations. So the whole idea that I install my private internet by having an application is something that really goes down really well. And we also like the idea of moving from the mobile terminal experience as we know today, everybody has a smartphone, to something that inherently disintegrates into distributed experiences. And that's the reason why we made that leap. But generally, I feel, obviously, that the points also apply to general microservice use cases itself. As I said, we interpret available compute resources as these Pico micro data centers. They can be dedicated compute resources. In the demo we gave this year, we played the scenario in an entertainment scenario in a hotel where the compute resource was provided by the hotel for hotel guests. So in that case, you might really have a compute rack downstairs, right? But Pico data centers could be home devices. It could be another user's smartphone. We also actually, in the use case, jumped on somebody else's smartphone. The smartphone was plugged in, so therefore it was a suitable data center. If it wasn't plugged in, it wasn't chosen because you don't want to jump on somebody who runs on battery. We believe that the proposed Coinrg would be a really, really good platform to actually discuss some of these issues, bring them together, evaluate them, but also obviously link to ongoing efforts. A lot of these efforts are ongoing in other working groups, and therefore bringing them together and probably also, get more people involved in the discussions is a really, really good thing. Some of the comments that I put on the list were already related to that, so there were a couple of things that I had sent to the list. The next steps, and personally I really hope that the proposed research group is indeed approved, we plan on doing is to update the draft with more information on the ongoing work, so be quite clear of what's going on. As there are references in, but we haven't really described in detail, but also provide an overview of other realizations. Because currently we are referring to a lot of things that we are involved in. There's other things. And also we plan on demonstrating realizations maybe at an upcoming meeting so people can see these funny microservices bouncing about. Thank you.
Time for question? Dirk Kutscher, one question. So for the service training implementation, what are the information units those functions actually operate on? Are you terminating some application layer protocol or?
So one of the reference that we have in the draft is to named service function chaining. So we actually extended, or we proposed to extend service function chaining, which we saw in the presentation before, on an entire name basis. So you issue URL-based requests rather than IP-based requests. And the service function chain, as was presented in the service function chaining one before, is always associated with some form of control. We don't use a manual control, obviously. Our service function chaining is defined in the application. So the application, in the application design, you specify that micro chain of, R, P, D, etc. And we're also looking at the frameworks that automates that, and therefore essentially constructs for you an actual named service chain, which is then translated into an NSH, which then is pumped into a named service function.
Right, and what are these functions actually receiving or sending? So what is it? Is it a flow of packets, or how does it really work?
The draft at the moment outlines the packet is the actual HTTP request. So it's not an IP packet because it's at the named level.
I get it. Okay.
Yeah. So HTTP at the moment is the example for a named exchange.
Thank you.
In the sake of time, let's move more discussions to the list. We're sorry. It's not anything against you, Jacob. Okay. We have our last presentation. This one is was a late addition to the agenda, so it's only 5 minutes, just for you to say a little bit if you want to. Yes.
Okay, hello everyone. This is Peng Liu from China Mobile, and I was talking about the new draft requirements of computing in the network. So as we all know, computing in network becomes a new trend to meeting the needs of emerging business. What needs to be computed and why? There are several problems need to be considered, such as the traditional network protocols only optimize traffic, which can't guarantee the latency or packet loss rate. And the centralization of computing resource is not efficient. And for different business, they may need different kind of computing. And there are little interaction among users of applications and networks, which brings that they don't know each other's requirement and capabilities. So some work has begun to consider these issues, but more requirement was to be considered. And the number one requirement is deterministic network capabilities, which include the latency and the packet loss rate. So for the latency, it's the concept from in time to on time, which means the latency is not necessarily the lower the better. It's just like a two-sides agreement and synchronization. And for the packet loss rate, it includes the time-varying routing, which found the link time very regular based on AI and predicting the network performance. And there are also other technologies such as segmented retransmissions to enhance to achieve segmented retransmissions. And the number two requirement is computing-aware scheduling. In this model, computing is seen as a link state, and the computing resource information is exposed. So according to the business requests, dynamic computing power matching is carried out based on network status and performance of computing resource to achieve optimal user experience and network utilization. And the number 3 requirement is function-based addressing. For the traditional IP-based addressing, it might bring some problems and which can't guarantee the such as the latency. So in the new function-based addressing, the application components distracted to on the server side are distributed on the cloud platform, and the business logic in the server is transferred to the client side. And the client only needs to care about the computing function itself, so as to realize the function as a service. And the last requirement is network programmability. So in network programming, the resource of network and the computing information can be transferred by network to users, so as to the requirements of the information transmitted by user to network. So the network can configure parameters according to the user's needs and the user's transfer requirements based on network capabilities, which could efficiently support the future application. So in the next steps, more requirements might need to be analyzed considering the computing capability, and some offline discussion about the related technologies may also need. And thanks. Any other comments?
So actually, this is just a little bit of historical stuff. The original spec for ISIS had a per node cost of traversing that node, which was called the hippity cost. So your packets would go hop, hippity, hop, hippity, hop, hippity, hop. And back then we took it out as a gratuitous complexity because there wasn't much difference between the cost of forwarding a packet on one node versus another node. It may be time to bring that back.
Okay. Thank you.
Thank you very much. Thank you very much.
Okay.
So we have just a few more minutes. So we intend to have a virtual interim probably in early October. We'll do an email poll. And we would like to address probably the last version of the charter and hopefully a set of milestones. I get the message from Dirk, the first Dirk K, about having milestone where you're still a proposed RG, but we kind of like the idea of focusing the work. We obviously are going to meet at IETF 106, which will be our third meeting, and hopefully will be accepted before that. And thank you so very much for everybody who came and for all your support. Actually, I think we're calling themselves the GEMS, so that Jeffrey, Eve, and I are really happy of how this is going, and we really thank you for all your great work. Thank you.